We continue with the proof. Since G is a group, every element A in G has an inverse, which is A the power of -1 is in G, such that A the power of -1 multiplied by A is equal to E, which is E is the identity element. The first one is for the left cancellation law. We need to prove that if A multiplied by B is equal to A multiplied by C, then B is equal to C. First step is we just write A multiplied by B is equal to A multiplied by C. And then we will multiply both equation with inverse A the power of -1. And then the left we have A the power of -1 multiplied by A multiplied by B equal to A inverse multiplied by A multiplied by C. And then we will use the associative properties and we will get A multiplied by A inverse multiplied by B is equal to A inverse multiplied by A multiplied by C. And then as for the identity properties, if A inverse multiplied by A, we will get E. Here, we will get E multiplied by B is equal to E multiplied by C. By identity properties, we notice that B is equal to C. Thus, left cancellation law is proven. For the right cancellation law, it's just same with before, which is we need to show that if B multiplied by A is equal to C multiplied by A, and then we will get B is equal to C. Firstly, we need to multiply both equation with A inverse. But this time, we put A inverse at the back of the equation. So, we have like this. And then by associative, we change the position of the bracket. We will have B multiplied by open bracket A multiplied by A inverse close bracket is equal to C multiplied by open bracket A inverse multiplied by A close bracket. From the identity property, we will get A multiplied by A inverse is E. Therefore, B multiplied by E is equal to C multiplied by E. Again, with the identity law, we will get B is equal to C. Thus, the right cancellation law is proven. Next, we continue with the example, authentic example and also original example. Here, we consider the group G is equal to R positive under multiplication. The first one, we have identity element, which is E is equal to 1. Since A multiplied by 1 is equal to 1 multiplied by A, and then we will get A for all A in R positive. Next, inverse. For each A in R positive, the inverse A the power of -1 is equal to 1 over A, since A multiplied by 1 over A is equal to 1. For the left cancellation example, we will have A multiplied by B is equal to A multiplied by C, where ABC is under R positive. Then, we divide both of the equation by A, and then we still get B is equal to C. As for the right cancellation example, here we have B multiplied by A is equal to C multiplied by A, which are A, B, C is under R positive. And then both equation we divide by A same as before, and we will get the answer is B is equal to C. Therefore, this satisfied both cancellation law.
Solution for question 2. Proof number 1. Closure under addition and multiplication. For any AB in ZP, A plus B mod P in ZP and A dot B mod P in ZP. The sum of two integers modulo P is always another integer in ZP. Proof number 2. Associativity, addition and multiplication in ZP are associative because they inherit this property from integer. Proven number 3 is commutativity. Both addition and multiplication are commutative in ZP as they inherit this property from integer. Problem number 4, additive identity. For any A in ZP, A plus 0 equal to A. Problem number 5, additive inverse. For every A in ZP, there exists an element negative A mod P in the ZP such that A plus negative A equal to 0 mod P. Problem number 6, multiplicative identity. For any A in a ZP, A dot 1 equal to A. Last problem is multiplicative inverse. For every A in ZP where A not equal to 0, there exists an element B in ZP such that A dot B equal 1 mod P. So, conclusion, some ZP satisfy all the field axiom when P is a prime. Example for question 2. Using Z5, the set of integer modulo 5 where P equal to 5 prime number, element of Z5 is 0, 1, 2, 3, 4. Number 1, closure under addition and multiplication. For example, 2 plus 3 equal to 5 equal to 0 mod 5. In addition, close. For multiplication, close is 2 dot 3 equal to 6 equal 1 mod 5. Second is additive entity. The additive entity is 0. For example, 2 plus 0 equal 2 mod 5. 3 plus 0 equal to 3 mod 5. Next is additive inverse. Each element has an additive inverse such that their sum is 0 mod 5. Their additive inverse of 1 is 4 because 1 plus 4 equal to 5 mod 5. The additive inverse of 2 is 3 because 2 plus 3 equal to 5, 0 mod 5. Multiplicative entity. Multiplicative entity is 1. For example, 1 dot 2 equal 2 mod 5. 1 dot 4 equal to 4 mod 5. One is multiplicative inverse. Each non-zero element has a multiplicative inverse such that its product is 1 mod 5. The multiplicative inverse of 1 is 1 sin 1 dot 1 equal 1 mod 5. For inverse of 2 is 3 sin 2 dot 3 equal to 1 mod 5. Inverse of 4 is 4 sin 4 dot 4 equal to 1. So conclusion is Z5 0, 1, 2, 3, 4 form a field because it satisfies all the field axiom.